Swayam Prabha. Digital India. Educated India.
Okay, so again to reinforce, this was the picture of the almost MDP that you saw earlier. To complete the definition of the MDP, we also need to specify gamma, okay, the discount factor. And so, I mean, I'm just arbitrarily saying this MDP has gamma equal to 0.9, all right? Okay, so these are terms that you need to be very familiar with through this course, okay? So I'm just writing down explicitly. V pi of S is called the value of state S under policy pi. Okay, some people might call it the utility rather than the value, but it's value, right? It stands for a long-term thing as opposed to reward, which is a one-step thing. And if you just take V pi, right? That's called the value function of policy pi. So V pi is, you can think of V pi as a function in the sense that if you give it a state, it will give you the value of that state under this policy. Okay, so V pi is called the value function. Good. So by virtue of what you've seen so far, right, maybe the intuition you have is we would like to have policies that have large values in some sense. It's good to have trajectories that give us a lot of reward, right? And that's what's defined in terms of the policy's value. But there is a slight tricky element here because think of it, right? A value function is not like a scalar. It's not one number. You can say that 23 is better than 21, right? But if you have two vectors, right? I mean, ideally you want all of their elements to be large, right? If they are values. But it could well be that there are two values, two policies. One is better for one state, another is better for another state, right? So although we would like to have policies which have large, good value functions, it's not very clear how to make this explicit. Okay, but we can, and that's what's coming to you in a relatively short section 2. Okay, so what we're going to do right now is to say that there is actually a well-defined problem to solve. Okay, and that problem is what is called the MDP planning problem. What is that? So let's again go back to our example MDP, and I'm not going to tell you right now how I did it, okay? But using the knowledge that I have, I actually went ahead and calculated the value function of each of the 8 policies for that MDP, right? Remember, you could do one of red and blue for each of 3 states, right? So there are 8 possible policies. So RRR means R at S1, R at S2, R at S3, etc. And so let's just look at one particular line, right? So if you take red at S1, blue at S2, and blue at S3, then this is like mathematically correct, okay, up to maybe floating point precision. The expected long-term reward you will get starting at S1 is 2.76, starting at S2 is 4.48, starting at S3 is 3.48. Okay, and I have calculated similar numbers for all 8 of these policies. So if I show you this picture and ask you, all right, now you tell me which policy you like, all right, which is a good policy to follow. You stare at this picture long enough, you will notice that there is this one policy, okay, that takes blue at S1, blue at S2, red at S3, that has this property that regardless of which state you are starting at, it has the highest possible value, right? So if you look at the first column, which is the best you can get from S1, right, following any policy, well, by following this policy, you can get 10, and you can't get more than 10 anywhere else, right? Similarly, second column is maximized by 11, third one by 14.45, okay? So, I mean, looking at this, it's quite clear that if this was our MDP, right, and you had to decide which policy to follow, BBR would be the best choice, right? Because you can't do better than BBR regardless of which state you have started at. Okay, so in some sense, BBR is therefore an optimal policy. So there's good news. Okay, so the good news is we didn't just get lucky on this particular MDP and find that there was an optimal policy. It can be shown. Okay, and in fact, this is something we will show in week 5, that every MDP is guaranteed to have an optimal policy By that, right, we mean it will have a policy pi star, which is such that you take any policy pi and you consider any state S, V pi star of S will be at least as high as V pi of S. Okay, so this is a non-trivial result, right? So we are comparing vectors, right? Literally functions of state to number. So in general, two policies need not be comparable, right? It could be that policy 1 is better at state 1, but policy 2 is better at state 2. There might well be policies like that, but we are guaranteed the existence of this policy pi star, which is such that it will dominate or equal every other policy on every state. Okay, which is why this needs proof, and it's something that we will do. It's not obvious, right? But the fact that we have this result, right? The fact that every MDP has an optimal policy makes life good for us, and we can formally define the problem that we are setting out to solve. Okay, so the MDP planning problem is this: you are given an MDP. Okay, so you're given S, A, T, R, gamma. So what does it mean when you're given this? It means you're given it, let's say, as a table or something like that, right? So S and A. So we can assume that you need to specify the number of states in S, the number of actions in A, that's N and K. Let's assume both of them are finite. And then T is going to be like a table with N squared K entries. Okay, it's got N squared K probabilities. R similarly will have N squared K numbers maybe. Yes, for every S, A, S prime, it needs to have a number, and gamma is just a scalar, right? You can be given all that. What you're supposed to do, right? The problem that we are solving, the MDP planning problem, is that of being given an MDP as input and computing an optimal policy for that MDP. Okay, we just said that every MDP will have an optimal policy. So the computational problem, given an MDP, finding an optimal policy, if you have an algorithm that does that, that algorithm is solving the MDP planning problem. Okay, it's a well-defined problem, and we're solving it. So, by the way, this is called the MDP planning problem. So planning has the meaning that you're solving a computational problem. Okay, so you are given all of these. You can read it in as a file maybe, and then your machine is churning away and computing an answer. Right? It's a computational problem. There is no learning aspect over here. Okay, so MDPs can also be used in the learning setting. That is something that we will encounter a little bit later in this class. For now, we are solving just a computational problem, and that's called a planning problem. So a few comments before we become more familiar with MDP planning problem. So I told you every MDP is guaranteed to have a policy. In fact, every MDP is guaranteed to have a deterministic, Markovian, and stationary optimal policy. Okay, so this is the reason it sufficed for us to consider only policies that are deterministic, stationary, and Markovian. You could well have optimal policies which are stochastic, right, which are non-stationary, which are non-Markovian, right, but you don't need them. Okay, what you're doing is looking for an optimal policy for an MDP. It's enough for you to be looking only at policies that are Markovian, stationary, and deterministic. Okay, so in fact, this is a part of the result that we will prove next week, or maybe the week after. Okay, so maybe I got ahead of myself saying we'll do it in week 5. It might go to week 6. Another comment is that every MDP is guaranteed the existence of an optimal policy. It can have more than one optimal policy. It can have more than one deterministic optimal policy, in fact. Okay, so that's okay. All right, all we need is to find one of them to satisfy the requirement of the MDP planning problem. And one other interesting aspect, again, these are all things that you will become familiar with being able to prove, okay, is that even if an MDP has multiple optimal policies, it will so happen that all of these optimal policies will have the same value function. Okay, so you might do a thing differently from a particular state. There might be 2 actions that you can take from a particular state, both of which are part of an optimal policy, right? But both will give you the same expected long-term reward. Okay, so this unique value function that belongs to all the optimal policies of the MDP, that is usually denoted V star. Okay, so star is good. Okay, so the optimal policy that we've chosen is pi star. Its value function is V of pi star. which is also sometimes called V star. Good. So that's the problem we want to solve. We're given an MDP, and an MDP is a way of encapsulating decision making that needs to result in long, fruitful sequences. Okay, so sequential decision making, and there are multiple ways in which an agent can make decisions encapsulated as policies. The result that we've not proven but we have claimed is that every MDP will have an optimal policy, and the problem we want to solve is that of computing that optimal policy for any given MDP. Okay, so what's coming up next is some variations of this basic problem formulation. Okay, so what we've defined is okay, and this is in fact the convention that we will go with. But surely you're going to also encounter literature around MDPs where you will see some departures from what we have taken as a given. Okay, so let's consider some of those and get them out of the way before we really move forward with our algorithmic development. Please don't be totally surprised when you look at the literature and you notice that things are looking a little bit different from our definitions. I'm just going to take you through some variations that you might encounter. So the first has to do with our definition of the transition and reward functions. So remember that we said the transition function given a state and action will give you a distribution over next states, and the reward function will associate each triple, right, state, action, next state with the reward that you get, right, a number. So you might see these other ways of formulating the problem. So sometimes, right, R of SAS prime, which we are taking as a number, right, might itself be treated as a random variable. Okay, it might be that when you take action A from S and go to S prime, you're going to get a random reward. Okay, and that random reward is R of SAS prime. So normally you will still assume that that reward is bounded, again say between minus R max and R max. But the variation coming up here is that the reward is not deterministic, the reward is also stochastic. Okay, that's not a really, that's not a big deal. Okay, so in some sense, if this is what is happening, what we have defined as reward, right, should be taken as the expectation of this random variable. Okay, so as we go along, right, you will sort of build the confidence to manage with some of these variations. Let me just go through the other ones as well. So sometimes you're not given a reward for state, action, next state. A reward function simply takes state and action and gives you a reward, numeric reward for that without looking at the next state. So that is also okay. So sometimes the way rewards are specified is, doesn't matter what state and action you take, as long as you reach a particular state, you'll get a reward that is associated with that next state, right? So you go from S to S prime by taking A. The reward is just given by R of S prime, okay, rather than R of S A S prime. Okay. Yet another variation. In fact, the recent version of Sutton and Bartow, I think, mentions this. You don't have separate transition and reward functions, but these are combined into a unified function that generates both, right? So this function here, right, gives a probability of both S prime and R, like a joint probability for next states as well as rewards conditioned on your start state and the action that you took. Again, something that can be managed. Another convention that you might notice, right, especially if you look at the literature from control theory and engineering. So we say an agent gets reward and you want to maximize values. There are other communities that say that the agent incurs a cost, okay, one step cost for each action, and it wants to minimize expected long-term cost. Okay, so that is easily fixed by just taking cost to be minus of reward, right, or just negating one or the other. So these are all relatively minor departures which can all be handled without too much fuss. They might need some work, okay, but they don't really take away from the sort of techniques and methodology that we're going to develop as we take this forward. So summary, you might encounter different definitions. It's okay, okay, you should know how to handle them. A second different aspect is something that is not so trivial. Okay, so in our definition, we considered what is called continuing tasks. Okay, an MDP which describes a world which exists forever. Okay, to infinity. So that is called a continuing tasks. Okay, in which like a trajectory of state action reward goes on forever. Many naturally occurring problems are modeled better as what is called an episodic task. Okay, an episodic task is one which will basically end. Okay, and once it ends, nothing else is happening on that task. And the way this is mathematically specified is episodic tasks can also be modeled as MDPs, but these MDPs will have a special state called a terminal state. Okay, also known as a sync state. So let's just call it S terminal. This is a state from which there are no outgoing actions. Okay, so here's a picture of an episodic task. Okay, so you notice that there are these two non-terminal states, S1 and S2, but there is this terminal state. Once you come into this terminal state, there's nothing to do. Okay, life is over. Now, if you have an episodic task, so usually it's only meaningful to do anything with that episodic task if it satisfies an additional constraint. Okay, and that constraint is that every non-terminal state in the episodic task, regardless of which policy you are following, must have a finite probability of, finite meaning non-zero probability of reaching the terminal state, okay, in a finite number of steps. So, I mean, you can have a terminal state. Suppose nobody goes into that terminal state, then, I mean, it's not really a proper episodic task, right? Because you can have infinitely long trajectories. But if this condition is also satisfied, then almost surely, right, every trajectory will end in a finite number of steps. So, and that is, necessary, right? Because, I mean, that is the whole point of having an episodic task. It's an episode, right? If it ends. Okay? If it doesn't end, it's sort of continuing forever. So episodic tasks are something that we will encounter as a part of our course. Okay, we will model some applications as episodic tasks. So when you are encountering an episodic task, right, you just need to make sure that you can guarantee this, right, that regardless of what actions you're taking, right, you will, with non-zero probability, go to the terminal state in a finite number of steps. So you can look at this MDP itself and see that it has that property, right? So if you're taking red from S2, right, you're going into ST with some chance. If you're taking blue from S2, you're going into ST with some chance. From S1, you're not directly going into ST, right? But with whether you're taking red or blue, right, with non-zero probability, you're going into S2, right? So again, from there, there's a chance of going into ST. So this is a genuine episodic task. Okay, we can work with a task that looks like this. The third topic to discuss in terms of variations is the very definition of what is the value of a policy starting from a state. So here's the definition that we went with, right? This is from one of the previous slides. And this definition of value is that of what is called infinite discounted reward. Okay, we are using discounting, but taking a sum that goes to infinity, right? So there are other choices here in how you define a value. So one other way of doing it is what is called total reward. Okay, so total reward is, again, it looks like infinite reward, but without discounting. Exactly what we said was problematic, right? Total reward is only meaningful to use when we are applying it on episodic tasks, right? So if the task itself gives us the guarantee that episodes are not going to last forever with high probability, then we can, just take the sum of the rewards. Okay, so infinite discounted reward and total reward, you can think of them as the same thing because you can implement total reward by just setting gamma equal to 1, right? Mathematically, that's the only definition. Only thing, we have to be a little bit careful when we are using total reward. Okay, we have to make sure that the task is episodic before we go ahead and do this. All right, so we will use both of these, by the way, as a part of our further development of the topic. Finite horizon. Okay, this is a much simpler sort of definition of reward. As the name suggests, you don't look at an infinite sum. Okay, so finite horizon reward is defined by saying that the value of state S under policy pi is R0 plus R1 plus R2 through some RT minus 1. Okay, so capital T is what's called the horizon. So you just count the expected reward for the next T steps. Okay, and T is a finite number. So rather than giving gamma as an input, right, you are given T as an input when you are asked to maximize finite horizon reward on an MDP. All right. One thing to mention, okay, is if the definition of values is that of what you get by doing finite horizon reward, then an optimal policy under this setting, right, it need not be stationary. Okay, so an optimal policy for a finite horizon MDP will, in general, do better by remembering how many time steps have elapsed. Okay, which is also proxy for how much more of the horizon is left. Okay, so this is a small technical detail. We will not be dealing with finite horizon much as a part of this course, nor also will we be dealing with the fourth type of definition of values, which is called average reward. Okay, so the average reward is a little bit more nuanced than what I am presenting here, and again, it is something we will not be getting into. But average reward is a very elegant formulation of long-term value, where the value of state S under pi is defined to be the average reward that you will get. Okay, but average over what, right? So let's take the average over the first m steps. Okay, starting at state S, right? Just look at R0 plus R1 plus R through m minus 1, which is m steps. But take an average. Okay, divide that number by m. That tells you on average how much you are getting over these m steps. Take the limit of this as m goes to infinity. Okay, make that m larger and larger and larger. This limit will be well defined. Okay, and define this quantity to be value of state S under policy pi. Okay, so there is a little bit more to average reward which I'm consciously not getting into over here. So if you're using average reward, think about it, right? You don't even need to specify a discount factor or horizon or anything like that. You just need state, action, rewards, and transition function in your definition of the MDP. Okay, which is why I think it is elegant. It is quite consistent with what you might want to achieve in many tasks. But technically, it is a little bit different from infinite discounted reward, and we will not be getting into it. Okay, so the summary from this slide is there are alternative ways of defining what is a good policy, what is the value of a state under some policy. Infinite discounted reward and total reward, more or less interchangeable just by varying gamma, and except you have to be careful if you're setting gamma equal to 1. Make sure that the task is going to terminate. Finite horizon and average, also legitimate choices, which we will not go into too much as a part of this course. Okay, so what did we do in this section? We covered a few variations of the definition of MDPs, of tasks, of values that you might find in the literature. So don't let that, discourage you or give you the sense that it's something new that we have not covered. Most of these you should be able to, I think, manage. Once we made some progress with MDPs and you have some experience, you'll see that there are only small changes that need to be made to accommodate many of these differences. Okay, good. So last 3 sections have given you a fair amount of theory behind MDPs. We formalized the definition. We formalized the problem of MDP planning. I've told you there are some other variations to it. But how does this make a difference to life, to applications? What is really the practice of MDPs? So to build some familiarity, I'm just going to give you a few examples, okay, of tasks that agents perform that can be viewed through the prism of an MDP. Okay, so let's start with this. You see there's a blue sky, there's also a blue helicopter. So imagine that you want to have an agent that can control a helicopter. Okay, so you have to be more specific, specify what you want to do. Maybe you want to follow some trajectory, or you just want to hover in place. So let's just take the task of getting a helicopter to hover, okay, in place, which means just be at the same spot. Can we formulate this as an MDP? If we do, then how? So the answer to this question and also the answer to the questions in the subsequent slides are not fixed, rigid. There's no correct answer. This is a design question. Okay, there's multiple ways in which you can do it, but here are some of the questions that you need to answer and settle. Will you frame this as an episodic task or a continuing task? Right. First of all, so remember, an episodic task is one which is going to end. Okay, a continuing task can basically go on forever. Now, you might think, the helicopter is eventually going to run out of fuel and it's got to come down. So you can model this as an episodic task. If you so want, you can do that. But see, normally you will not be operating a helicopter in a setting where there is a risk that the helicopter is going to run out of fuel and fall down or something like that. Okay, so maybe you will have some envelope right around this whole control, which makes sure the helicopter is not going to do something disastrous. Okay, so if you're somewhat guaranteed through an outer loop that the helicopter is more or less going to be airborne, right, then you can maybe formulate this as a continuing task, right? Even if it doesn't go on forever, right? If it goes on for 10 million steps, in practice, you can view it as a continuing task. And why would this go on for 10 million steps? It really depends on the frequency with which you're applying the controls, right? If you're applying controls every 10 milliseconds or something like that, or even 10 times a second, let us say, right? That's once every 100 milliseconds. If you're doing this for a few hours, right, that's going to run into thousands, tens of thousands of controls, right? Such a long horizon can basically be thought of as forever in practice, okay, not in theory. Okay, what are states, what are actions, what is the transition probability, or like what are rewards, etc. So this comes from physics, right? Any body that is rigid body that is in space, right? You need 12 parameters to describe it. Okay, you need its let's say x, y, z to say where in space it is, and then you need to also specify its rotation. Okay, about 3 axes. So when it is a helicopter or an aeroplane, these 3 are usually called roll, pitch, and yaw. Okay, so those are 6 degrees of freedom, and you typically also specify the derivative of each of these quantities with respect to time. Okay, like velocities or angular velocities. So you have like a 12-dimensional description of the state. Okay, as a physical entity. You might want to also include other things in state, right? Like how much fuel is there maybe in the helicopter, other aspects which you can sort of measure and which you think are relevant to deciding the future, what's going to happen. Actions, okay? So a helicopter, you will notice here, has 2 rotors, okay? One on top and one by the tail, which is not actually very clearly visible, I think, over here. But most helicopters will have 4 control signals. Okay, you can specify both the current or torque and the angle. Okay, for each of these rotors. So that does not mean you have 4 actions. Okay, what this really means is you have an infinite number of actions, because the amount of current you can pass, that's like a continuously varying quantity, right? You have a 4-dimensional action. Okay. And if you want, you can discretize these dimensions, and you'll have, if you do a cross product, a very large number of actions that can be applied in a helicopter. Okay, from a particular state, if you apply a particular action, what's going to happen, right? So this is probably not something that you and I can write down as a few equations, but this is the laws of nature, right? Laws of physics. Maybe drag is going to act in a certain way, and friction, right? The actual amount of torque you're generating will create some lift, etc. Right? So for now, right, I'm just asking you to think in these terms. So don't think more specifically about how you're going to actually encode all of this information. Maybe it's not that easy. Okay. What about the reward function? This is really where you need to try and understand. Okay. So if your objective is to keep a helicopter airborne at the same point, right? Then what is the right way to reward it? So here's what you can do, right? So there's a target position, let's say X, Y, Z, roll, pitch, yaw, and the helicopter at any point of time is going to maybe deviate from that a little bit, right? So how about taking the difference vector between your target and current all right? Looking at the length of that vector and maybe squaring it, right? Or taking like a positive length, okay? And doing the negative of that and calling that the reward, okay? So what am I saying? You're in some state, okay, which is, let's say, some distance, okay, away from your target position. And then you go to another state, which is again some distance away from your target position. If the distance has become less, right, you should get some positive reinforcement. Or if you've actually gone all the way, right, you should get positive reinforcement. On the other hand, if you're going away from your target, you need to get negative reinforcement. Okay, so if you can encode this in some way, right, there might be multiple ways of doing it. Then maximizing expected long-term reward will then align with our objective of keeping the helicopter airborne in the same position, right? Because if you're deviating, then your reward is becoming less. You need to apply controls in order to keep the helicopter airborne at the same spot. Okay. What about gamma? If this is actually a continuing task, you need to set some value of gamma that's less than 1. Okay. Otherwise, when you're calculating, things will diverge. It's not okay. So in practice, people will tune gamma to be, I don't know, 0.99, 0.999, something like that. Okay. Usually it's like an empirical thing. Okay. So that was example number 1. Look at the reference, by the way. Okay. That's a paper from 15-20 years back on the application of reinforcement learning for helicopter control, okay, where actually the first step is to model it as an MVP.